Today, we're starting mini lecture 8, and we're going to cover mesh analysis. So let me share screen. And often when I talk about mesh analysis, I'm going to find essentially myself comparing to nodal, because in essence, these are the two methods that you are required to have proficiency in the course. So making the parallel, and at some point, we'll solve problem using the two methods to help you see the parallel very well. So let's share a screen here. So mesh is the order, what we call the order method. And part of the reason of calling it the other method, because it's slightly less general than nodal. Nodal has no restrictions. Software uses nodal analysis to solve circuits. Mesh has one restriction. It requires that circuits are planar. When we say circuits are planar, we're talking about circuits that basically can fit on a piece of paper. So no 3D wires like this. So anything that's like this is assumed to be touching. So planar circuit, for purpose of this course, this is more than enough for us to solve the circuits that we have. But nevertheless, it is a restriction that you need to know. What I want to say to you is that you are required to have proficiency in both mesh and nodal. In this course, particularly in the earlier part of the course, I'm essentially going to ask you use nodal to calculate the voltage or current here and there, or use mesh analysis to calculate the current or voltage or power here and there. In some part later on in the course, you may have options where you're looking at a circuit and I ask you to calculate voltage and current, and you make a decision. Do I use nodal or do I use mesh analysis? But probably in the earlier part of the course, given that a major foundation of the course are these two methods, I want to make sure that you can do both equally well. So often I get a few students that think, oh, gee, I can pick one and ignore the other. This is not the case. You will be required to essentially use those two methods interchangeably, at least in this course. So let's start with mesh here. So again, I will on purpose do a parallel with nodal. So if you think about nodal analysis, what are the unknowns? The unknowns are the node voltages. And the node voltage is the number of unknown is the number of nodes minus 1. So in mesh, we're going to define something called a mesh. A mesh is essentially a loop with no other loop inside. A loop that essentially is the smallest loop, so it has no other loop inside. All right. The mesh is going to be where our variables are going to come. In fact, in mesh analysis, our variables are the so-called mesh currents. Of course, I'm going to show you what that is shortly. As we did for nodal, when we do a couple of circuits, so today what I'm going to do essentially is myself do a couple of circuits, and then I'm going to ask you, I'm going to put one and ask you to pause the video or stop it and try to do it over 25 to 30 minutes and come back and look at the solutions, okay? So first category, if you think about nodal analysis, what did we do for nodal? We looked at circuit first with no voltage sources. Then we learn how to handle voltage sources later on. Mesh is going to be almost the opposite of what we did for nodal. We're going to look at circuits that have no current sources. That's the category. In mesh, current sources require special treatment. In nodal, voltage sources require special treatment. Okay, so the first category, what I call the basic mesh analysis, is circuits with no voltage sources. And then the next lecture, I'm going to overlay how do we treat current sources in mesh analysis, just very much we did with nodal analysis. We overlay how do we treat voltage sources onto the basic nodal analysis. So the first thing we're going to do, I'm going to basically give you this procedure. An announcement will follow with some graphics to help you out here. But when I do the example is really when this thing comes, really become grounded, if you will. We're going to identify all the meshes. Okay, we're going to identify all the meshes. So this is kind of like identify the nodes. Students struggle at first to find all the nodes correctly in nodal. I don't usually have problem with students finding the meshes. The mesh tends to be more obvious to most of us. So we're going to identify all the meshes. Again, remember, a mesh is a loop with no other loop inside, so it's the smallest loop. And then we're going to arbitrarily assign mesh current, some textbook call it loop currents. We're going to call it mesh currents. We're going to assign mesh currents, and we're going to assign them arbitrarily, but we're going to make sure that we don't duplicate I1, I2, I3, and so on. Okay, so these mesh currents are going to be our unknowns. They're going to be the current we solve for. And we assign them to so-called finite meshes. What a finite mesh is essentially a mesh with no open circuit. Because if you had an open circuit, the current, of course, would be zero. Okay, so we assign mesh current to the finite meshes. So the next step is that for every passive element that doesn't have a voltage, we're going to insert a voltage, which means labels and polarities. We're going to insert a voltage. When I say passive elements, I'm talking resistors. That's the only passive elements we have. And we're going to call them V1, V2, and so forth, and V3 without duplication. Okay, so you can see the dual nature. So when we did nodal, what did we do with nodal? What did we do? We essentially selected node, and then we label node voltages. We label node voltages. Then we assign current on the passive element. We're doing the exact opposite. We essentially assign mesh currents, and the mesh currents are the unknowns to finite meshes. Then we put voltages on the resistors, on the passive element. So it's kind of a dual method, if you will, that we do that. The next step, so right here, this is what I call up to here, we prepare the circuit for a mesh solution. Those are the preparation steps, just like we did for nodal. So we begin the math, essentially, method here. We're going to write a Kirchhoff voltage law at each of the meshes. Assuming we have M meshes, we're going to have M mesh currents. We're going to have M unknowns. Then we're going to write M Kirchhoff voltage law, KVL, one in each mesh. Okay. So these KVL equations are going to be required to be written in terms of voltage, just like your KCL equations were required to be written in terms of current. Then for each of those, we're going to essentially write Ohm's law. What Ohm's law does in mesh analysis allows us to go from voltages to the mesh currents. Then we put these Ohm's law into the KVL equations. We collect terms. We solve for the mesh currents. Okay, we're going to practice that. I'm going to give you 2 problems to practice, and then you're going to get an announcement that describe this thing a little bit, more details later, and then you'll have obviously some practice problems in the future as well. So let's look at as basic of an example as I can find. The reason is because, well, I could find one mesh. I could do a one mesh problem, but this is a 2 mesh. And there is a reason I'm picking the 2 mesh. You'll see that very shortly here. So this problem is asking to calculate the power absorbed or produced by each element. You probably now getting to be comfortable with that statement. This is a clear thing. I like to ask for power. So typically in Engineering 17, you're going to be asked for voltage, current, or power. So these are the 3 things that we ask. That's essentially the circuit responses, the important circuit responses, particularly voltage and current, because once we have voltage and current, we can get power. Okay, so I am looking at this circuit here. I'm hoping it's obvious that you see 2 meshes here, one in here and one in here. Okay, these are finite meshes. What do I call finite meshes? They have no open circuit. In other words, as I go around the mesh, I'm going around elements. There's no open circuit. Okay, so let's begin here to see how we solve this problem, just to learn the process. I'll do a second one to try to reinforce, and then I'll hopefully get you to do one yourself. So these are the 2 meshes, again, a little bit more elegantly shown here in orange. Okay, a mesh is a loop without a loop inside. So basically here, if you look at this, you have a big loop here, and this big loop here has 2 meshes inside. Okay, so that's what I say. A mesh is a loop with no other loop inside. So these are the 2 meshes. In the past, at least in my experience teaching this course, students typically don't have problem identifying the meshes. Some students have problem identifying nodes, not the meshes. Okay. So the next step, we are assigning mesh currents. We are assigning mesh current to each mesh. Essentially, mesh current is a loop current in the mesh. We are assigning mesh current here. That means here, under 20 volt here going up, the current I1 is going up. Okay. Also on the 3 ohm, the current I1 is going to the right. Okay. Similarly, for the 4 ohm, the current I2 is going this way. That's I2, and I2 is going down to the 10-volt source as well. Okay. So that's what that means when we assign those mesh currents. I typically, the direction of I1 and I2 can be clockwise or counterclockwise individually. It's up to you. What I tell students, however, pick one direction so that you're not thinking, where is this current and how is the current going? I tend to pick one direction for all the current, but strictly speaking, you can pick them individually. It's quite correct. Okay. So again, this is stating that the 20-volt resistor and the 3 ohm are getting the current I1, the 4 ohms and the 10-volt getting the current I2, and this resistor, the 2 ohm resistor, is getting a combo current. Okay, it's getting both a contribution of I1 and I2. For example, if I want the current going this way on the 2 ohm, then it's I1 minus I2. And it is I1 minus I2 because I1 is going in the same direction of the current I'm looking for, and I2 is opposing it. Okay, if on the other hand, just clean it a little bit, if on the other hand, I want the current going this way on the 2 ohm resistor, it will be I2, because I2 is going in the same direction of that current, minus I1. Okay, so what you are seeing in mesh, when you have elements that are between two meshes, in the case of the 2 ohms, so you have to make sure that that element sees both currents. Okay, so this is why I did not pick a one mesh circuit, that I wanted a 2 mesh to make sure that that part is included in the discussion. Okay, then we assign voltages on our passive elements, on our resistors, if they do not have voltages already assigned. I keep saying that. So V1, V2, V3, where you put your plus and minus, entirely up to you. You can put them left or right or left, up, down. There's no wrong or right way. Okay, so we assign that. So at this point here, we've prepared the circuit for solution. So the circuit is now prepared for solution. I have 2 unknowns. My unknowns are going to be I1 and mesh I2. I'm essentially going to write 2 KVL equations, 1 KVL equation in mesh I1, 1 KVL equation in mesh I2. Okay, so let's go about it. So KVL in mesh I1. So what I tell students essentially when you're writing KVL, I say pick a rotation, pick a direction of rotation. Okay, you can pick it clockwise or counterclockwise. It doesn't have to be the same direction of the mesh current, although it can be. You can pick either the way the mesh current is or the other way. It doesn't matter. But if I pick a direction of, and I'm looking at KVL in mesh I1, the first sign you find for the voltage, put it as a sign of the voltage. So I'm going to say plus V2, plus V1. This is, I'm going along clockwise. Okay, plus V1, so plus V2 plus V1 minus 20 volt equal to 0. So that's going in the same direction as mesh I1, okay, which is the equation that I have. If on the other hand, I go opposite direction, which is quite fine as well, okay, I can start here and I say I go opposite direction. The sign that I find for the voltage is the first sign is what I put as a sign of the voltage. So minus V2 plus 20 volt. So plus 20 volt minus V1 is equal to 0. You basically get the negative of the equation. Perfectly correct. So either way, just pick a direction. The first sign you find for the voltage is the one you put down as a sign of the voltage. Okay, so that's the KVL. Similarly, in mesh I2, you get minus 10 volt, minus V1 plus V3 is equal to 0. So these are my 2 KVL equations. These equations are in terms of voltages. So depending on where you put your plus and minus, you're going to have different equations, but still very correct. Okay, so your plus and minus essentially determine what the equations are, where these voltages are, but still very correct. I want the KVL equation to be in terms of voltages. You will see on the web, you will see on YouTube, there are instructors that do it differently. I will grade you based on that. Okay, so 2 kVL equation in terms of voltage. So what we're going to do next is Ohm's law. We're going to do Ohm's law. And what Ohm's law allows us to do is go from these voltages on these resistors to the mesh currents. And anytime we do Ohm's law, we need to think about one convention, the passive sign convention. So here are the Ohm's law equations here. So I want you to pay attention when you have an element that's between two meshes. The 2 ohms here, between two meshes, okay? Because once you have an element between a resistor between two meshes, it needs to have both currents in there. So for V2, so V2, again, the current I1 is entering the positive terminal, so following the passive sign convention. So V2 is 3 times I1. For V3, I2 is also entering the positive terminal, the way I have it. So V3 is 4 times I2. And then, of course, for V1, it's going to be 2, the resistance, times the current that's going this way. And the reason I picked the current up so that it satisfies the passive sign convention. So given that the current that's entering the positive sign, so it is I1, so 2 times I1 minus I2. Okay, so we need to satisfy the passive sign convention. So there are 2 things that I want you to think about when you have a resistor between 2 meshes. One, it needs to have both contribution from both currents. So make sure that. And then, excuse me, looking at the passive sign convention for each current individually. In this particular case here, that's why I draw the arrow here. This is the current that I'm seeking so that it satisfies the passive sign convention. So that becomes I1 minus I2. We'll practice this. That's the one little quirks that I think it's a little different as compared to nodal, and that you need to pay special attention to. At this point here, I'm going to take these Ohm's law equation, put them back into the 2 kVL equations and collect terms. So you get 2 equations to a node. When you do that, by the way, so students find that easier because you don't have to put under the same denominator. When you put these into the KVL, you're just adding terms because you don't have divided by, it's just current multiplied by resistance. So you just add things. It's a lot easier from an algebraic standpoint. And we get 2 equations to a known, and then we solve for these mesh currents. Okay. That, in essence, is mesh analysis for circuits with no current sources. We're going to do a second example just to kind of give you a little bit more complicated examples. But in essence, this has all of the pieces of the method for circuits with no current sources. Okay, once we have that, we can actually calculate power. Of course, in this particular case, I'm calculating the voltage for each resistor and then multiplying by current. So I'm using power is equal to VI. So for the 3 ohms, I first find the voltage and then multiply by current. That satisfying the passive sign convention. Same thing for each resistors. Okay. And of course, for the sources, power must satisfy the active sign convention. So the current must enter like this, enter the negative terminal, which I1 does. So it's really, for the 20 volt, it's 20 times I1. So it's a 107.7 watts. And for the 10 volt, it also satisfies the active sign convention. The current is entering this way. So it is 10 times I2. So we get that. So power generated again should be equal to power absorbed or dissipated in this particular case. Both of these sources are producing power, essentially. So let's take a moment to see this. Essentially, we're looking at a 2-mesh circuit to show you the basic step of mesh analysis with no current sources. We're going to go on and look at a little bit more complicated circuit, and then I'm going to ask you to do one. Okay, so we're looking at a second, a little bit more complicated of a problem, obviously, because we have, first of all, we have 3 meshes. And then we have a dependent source, just to make sure that we don't. And you will notice here we have 2 elements that are shared by meshes. The 3 ohm is between 2 meshes and the 4 ohm. So it makes things a little bit more complicated. And of course, the dependent source also is between 2 meshes. And this question is asking us to find the power either delivered or absorbed by each element. resistors and the two sources, the independent source is 6 volt and the dependent source is 3V2. We're going to set up the mesh. This is going to be a solid example. This is the kind of problems that eventually in an exam you ought to be able to do, that kind of complexity. Okay. So let's start here. So I prepared the circuit here. What do I mean prepare the circuit for solution? I've identified my 3 meshes. And then I put mesh currents, I1, I2, and I3. Again, you will see me do that most of the time. I pick one direction. In this case, I'm going clockwise. I could have picked counterclockwise. And then I label them sequentially, I1, I2, and I3. In mesh analysis, the mesh currents are the unknowns. Okay, so we have 3 unknowns, and I'm going to need 3 equations to solve for them. Then I add on my passive elements, my resistors, I add voltages, V1, V2, V3, V4, V5. Okay, where I put the plus and minus entirely up to me. There's no right or wrong way to do it. Okay, the passive sign convention is what's going to self-correct all of that. So the circuit is ready for solutions. What I'm going to do right now, I'm going to basically write a KVL in this mesh. Then I'm going to write a KVL in this mesh, and I'm going to write another KVL. So I'm going to have 3 KVL equations in terms of voltages. Then I'm going to do Ohm's law that help me convert the resistor voltages to mesh currents, put them in the KVL, and solve for the mesh currents. Then I can answer the power questions. So let's go at this. So these are the 3 KVL equations in mesh I1, I2, and I3. In mesh I1, again, I can pick the rotation, plus V1, plus V2 minus 6 volt equal to 0. I send the 6 volt on the other side of the equation, but it's plus V1 plus V2 minus 6 volt equal to 0. That's the KVL in mesh I1. Okay. In mesh I2, plus V3 plus V4 minus 3V2 minus V2 equals 0. Okay, so again, standard stuff. So I should also, let me go back to this and make a comment here. The given problem here, this problem had a dependent source that puts out a voltage. It's a dependent source, but it's a dependent voltage. It's a voltage source. It puts out a voltage that's 3 times V2. That was given in the problem, and the author essentially, i.e. me, I'd put V2 across the 3 ohm. That was given to you. So when we go ahead and prepare the circuit here, we basically use the V2 that the problem gives. You don't want to add another voltage on the 3 ohms because you already have a voltage defined on the 3 ohms. We just use it, okay? And obviously that determines those KVL. So KVL in mesh I3, then minus V4, plus V5 plus 3V2 equal to 0. So these are my 3 KVL equations in terms of voltages. Okay. Then I'm going to do Ohm's law. Anytime you're going to do Ohm's law, we're talking passive sign convention. Okay. So the Ohm's law essentially going to take those resistor voltage and convert them to mesh currents. Okay, let me show you some example of that. Every time you write Ohm's law, you need to ask where is the current entering. In this particular case for V1, the current is entering the positive terminal. So then V1 is 1 times I1. Okay. For V2, so you're going to need to pay special attention when you have a resistor or any element that's between 2 meshes. Okay. In the case of the 3 ohms, the first thing I want you to think, the 3 ohm is between 2 meshes. So I need to have contribution from both mesh currents. So I should have something for I1, something for I2. Okay. Then I ask myself, which one is entering? How is the current entering V2? The current entering V2, because I want the current to be this current. For the 3 ohm, I want the current to be this so that it satisfies the passive sign convention. So the current that's coming down the 3 ohm, just like I put that arrow here, it's I1 minus I2. Okay. So that's why you see V2 here is 3 times I1 minus I2. Okay. So just a little bit of just to make things a little interesting, if I had my mesh current like this, I2, then V2 would be 3 I1 plus I2 because both current will be coming the positive terminal. Okay, so just a side note here. So similarly here, V4 should have contribution on both mesh current, mesh I2 and mesh I3. And then I ask myself, how is the current? The current should enter like this so that it satisfied the passive sign convention. The way the current should enter with respect to how I define I2 and I3, then it is I2 minus I3. So you have V4 is 4 times I2 minus I3. Okay. And then, of course, the other ones are a little bit simpler. V5 is 5 times I3. And then V3 is 2 times I2. Okay. So that's the essence of mesh essentially, is basically writing KVL equations and then turning aside and writing Ohm's law with the passive sign convention. When we write KVL equation, it has nothing to do with the direction of the mesh currents. The KVL equations have nothing to do with how we select the mesh currents. It's when we do Ohm's law, then the mesh currents and the voltages where we put plus and minus, everything synchronized to get you a correct solutions when you satisfy the passive sign convention. So we're going to take those equations here, those 5 equations, put them in the 3 KVL equations and collect terms. And you can see collect terms means easier because you don't have to put under the same denominator. So we get out 3 equations, 3 unknown, and expecting you to use a calculator. And then essentially we get out 3 mesh currents, basically. Okay. So we're going to go on to calculate power for each element now that we have our mesh currents. And how we do this, of course, you know, nodal analysis gives us node voltages. If we use nodal, we get node voltages. If you use mesh analysis, you're going to get mesh currents. So typically for resistor, the best power formula for resistor, if you're doing mesh, is the resistance times the current squared, because you have the current. So you don't have to do something else. So I typically will use that power calculation when I am using mesh analysis for resistors. And if I am using nodal analysis for resistors, I'm going to use V squared divided by the resistance. Okay, just so you know, because it's just simpler. So I have the mesh current, so I'm going to calculate the power for each resistor. And that's what I do for that. And now we go on to the source here. Okay, for the 6-volt source, we have to satisfy the active sign convention, which I1 actually does. So the power for the 6-volt is 6 times I1. So 1770. So I didn't have to put a minus sign because it is entering the negative terminal. So how about the dependent source? It's a little trickier because, of course, the dependent source is between 2 meshes. So it needs to have both current. So I need, for the dependent source, I need the current that's going down this way, so that it satisfies the active sign convention. So the way I'm going to calculate the power for the dependent source, it's going to be the voltage, which is 3V2, times that current that I put, which is I2 minus I3. So it's 3V2 times I2 minus I3. So you have to calculate V2 as well. V2 is the voltage across the 3 ohms. Okay. And you can see that that's essentially the voltage across the 3 ohm is 3 times I1 minus I2, and then multiply by the current I2 minus I3. Okay. So that it's a little bit more complicated, obviously, than the first problem, but that's where I'm hoping you get there. But this really wraps up the 2 examples that I want to do. I'm going to put an example for you, and then I'm hoping you pause. And then you essentially allow yourself about 25 to 30 minutes to do it. So this is a problem that I have for you to do, and I'm hoping that you either pause the video or you absolutely stop it and you can restart it again and go to that location and you focus on calculating the 3 mesh currents. The power questions, you can do it a little bit later if you want. It's important. But what I want you to know, to be able to do right now, is to set up the problem correctly, write KVL equation, 1 in each mesh correctly, write the Ohm's law equations for each resistor, focusing on the passive sign convention, put them in the KVL equation, collect term, get 3 equations, 3 unknown. In this particular case, you can kind of see that we have a 3 mesh problem here, solve for the mesh currents. Then we can answer the power question. So I'm asking you to pause the recording and then take about half hour to do this. Okay, so let's go about setting up the mesh analysis procedure. This is a circuit with no current sources. So that falls into the class of circuit we're dealing with. Again, in the future, we learn how to treat current sources in mesh analysis. So let's go about it. So we prepare the circuit. We identify our three meshes. They are finite meshes, no open circuit. We put mesh currents. Again, I typically put them all going in one direction here, I1, I2, and I3. And then we assign voltages to resistors, passive elements that do not have a voltage on them. Okay. One of the things you should notice here, this voltage source here is a voltage source that depends on current, depends on the current IA. The current IA is the current on the 2 ohms shared in the mesh between the mesh I1 and mesh I3. Okay. So that's just things to note. So when you see a problem like this and you set up the problem, the first thing I kind of want you to think, okay, do I have elements that are between meshes? Identify them, because you will need to do some special attention, if you will. Not really special treatment, but special attention when you write Ohm's law for it. And in this case here, we have a 1 ohm here. The 1 ohm is going to have both mesh I1 and mesh I2 current. You got the 5 ohm here that's going to have both mesh I2 and mesh I3. And then I have the 2 ohm that's going to have mesh I1 and mesh I3. Just point that out to yourself, that you need to know that. At this point here, how many unknowns I got? I got 3 unknowns. The mesh currents I1, I2, and I3. I'm going to write a KVL in mesh I1, a KVL in mesh I2, and a KVL in mesh I3. Okay, so here are the 2 KVL in mesh I1 and I2. So in mesh I1 here, again, I can pick any direction of rotation. The first sign that I put that I find for the voltage, I put it as a sign of the voltage. So -5 plus V1 plus V2 equals 0. -5 plus V1 plus V2 equals 0. Similarly, for mesh I2, I can start here. I go 2IA plus V3 minus V5 minus V1 equals 0. Okay, the first sign that I find for the voltage, I put it as a sign of the voltage as I go around. Those are my 2 KVL equations. I need one more KVL equation in mesh I3, and there it is. Okay, it's plus V5 plus V4 minus V2 equal to 0. Okay. So these are my 3 KVL equations. This is 1 and 2, mesh I1, mesh I2, and then for mesh I3. Then we're going to go right to Ohm's law. Anytime we write Ohm's law, passive sign convention. And as I mentioned earlier, look at the resistors that are between the 2 meshes, because they need some special attention. In the case of V1, so essentially V1 is 1 ohm times I1 minus I2, because I need the current going this way in V1 so that it enters the positive terminal. That's V1. V2, I need the current that's going along the direction IA is going, because IA is satisfying. So it's going to be V2 is 2 times I1 minus I3. So you ought to be able to understand that at this point that the current IA essentially, this dependent source depends on IA. IA is I1 minus I3, because everything needs to be in terms of the mesh currents, everything. Okay. So V3 is 3 times I2. I2 is entering the positive terminal. V4 is 4 times I3. I3 is entering the positive terminal. And V5, of course, the 5 ohm is between mesh I2 and mesh I3. I3 is entering the correct way. I2 is entering the wrong way. So it's V5 is 5 times I3 minus I2. And of course, as I stated before, the current IA, and we're going to need that for the dependent source, is I1 minus I3. That was given to the problem, in the problem statement, the current IA. So I take all of these, put them in the 3 KVL equations, and then you get your 3 equations, 3 unknowns. Just like I've stated for nodal, if you get me those three equations, three unknown correctly, at least for the first month and a half in the semester, you will be given 75% about of the grade for that problem. So I am grading you on the process. Okay. Then we solve for these mesh currents. Okay. Then we, in a situation right now, we can calculate power. Again, when we're dealing with mesh analysis, we calculate mesh currents. The easiest power formulation is the resistance times the current squared for the resistor. But let me calculate the power for the sources. I1 is entering the right way. I1 is entering the negative terminal for the active sign convention. So the power for the 5 volt is simply 5 times I1, 9.8. For the 2IA, I2 is entering the wrong way. I2 is coming in the positive terminal. That's why you have this minus I2 here. Okay. So the power for the dependent source is the voltage that it puts out, 2IA times minus I2. And of course, we have to write IA in terms of the mesh current as well. IA is I1 minus I3. And we find that the dependent source actually has a negative power. With the active sign convention followed, when you get a negative power, you can conclude that the dependent source is dissipating power. It's acting like a load because it's connected in a way that it's essentially absorbing, dissipating power. So those are power for the source, and that concludes this exercise and also conclude our mesh analysis, this mini lecture for mesh analysis for circuits with no current sources. The next lecture, we're going to overlay how do we treat current sources in mesh analysis.